This lesson deals with lab number 3, which is Wheatstone bridge applications. A Wheatstone bridge is an instrument that is used to measure an unknown resistance, and it does this by balancing two sides of a voltage divider. It was first invented in 1833 by Samuel Christie. It was really improved by Charles Wheatstone in 1843. Let's take a look at the configuration of a Wheatstone bridge. Suppose to have 5 resistors, so R1, R2, R3, R sub S, and R variable. Suppose that I vary this resistance such that the current in this resistor is equal to 0. Okay, what does that imply? Well, let's write down that this is equal to 0. That means that the current in R1 is the same as the current in R2. Now, if you recall from ECE 201, that was the condition that we needed for a voltage divider. In other words, the voltage across R2 is going to be equal to R2 divided by R1 plus R2 times the voltage across them, which is our function generator voltage. The same is true on this side, that this current would have to equal this current because the current coming in here is 0. And again, that would mean that the voltage across here would just be our voltage divider rule, which would be R variable over R sub S plus R variable times the voltage V sub Fg. Now further, if the current in this resistor is 0, then the voltage across it is also equal to 0, because the voltage is equal to the current times the resistance, but the current is equal to 0. And what that implies is that this voltage equals this voltage. In other words, the rise in voltage would equal the drop of 0 plus this. We're going to use that to solve for what's called a balance condition on the next page. And so here's the voltage divider on the left-hand side equal to the voltage divider on the right-hand side when the current in the resistor R3 is equal to 0. What's interesting here is that the value of the function generator voltage drops out. So if this were a battery pack instead of a function generator, as the battery pack is aging, the results we're about to derive don't change. Let's do a little bit of algebra on this equation. Let's divide the numerator and denominator by R2. So I get a 1 in the numerator, and then I get R1 divided by R2, and then R2 divided by R2, which is equal to 1. Do the same thing on this side of the equation, divide by R variable. So you get a 1 here, divide this by R variable, and then likewise here, get a 1. That implies that this quantity is equal to this quantity. Let's write that down over here. Now, the balance condition is the following. If I were to cross multiply here, R1 times R variable is equal to R2 times R sub S. Now, I don't have to memorize this formula, but I like to know these things so that I can write them down quickly. And sometimes in lab, it helps me get through a problem quicker or a calculation quicker. Now, what is this? If you go back and look at the previous page, we have a balance condition when we vary this resistor such that this current is equal to 0, and that implies that R1 times R variable is equal to R sub S times R sub 2. Now we can solve that equation for R2 if R2 were an unknown resistor. So let's do that on the next page. So here's that balance condition. Now let's just solve for R2, which would be R1 times R variable divided by R sub S. So if we had measured the resistor R1, R sub S in advance, and R variable is actually going to be a collection of precision resistors configured with a switch, then if I pick R1 equal to R sub S, then R2 would just be equal to whatever R variable is. That would allow us to measure an unknown resistance by pre-measuring other resistors. And we could do that with a voltage source and an ammeter and figure out the exact values of resistors, then build an instrument. And in fact, that's what this was done as the first resistance measuring device. Here's a picture of a Wheatstone bridge, rather an old instrument. The way it's set up again is that R1 and R sub S are precision resistors set equal to each other, and R variable is a collection of precision resistors on parts of a switch, and when you rotate these switches, you actually get the value of the unknown resistance. And you vary the switches until the current in this meter goes to 0. This turns out to be a very, very precise technique if you had precision measurements on the resistors, so you can make it as precise as you wanted to. Although this is a very old idea, we still use this concept in many, many instruments. In fact, we're going to use this idea in our scope probes. Now, besides the resistive voltage divider, there's a thing called the capacitive voltage divider. It's the same idea. We'll put two elements in series. Now we'll put capacitors in series instead of resistors. And we're going to solve for the voltage across each capacitor. Now we'll be doing this in the frequency domain. So we've got a AC signal coming in here. So we've got a phasor voltage. And we're going to solve for the phasor voltages V1 and V2 across capacitors C1 and C2. Now because they share the same current, we can use the voltage divider rule. So it's going to be the impedance of this element divided by the impedance of the sum of the two times Vn for the voltage V1. Likewise, the voltage V2 is going to be the impedance of C2 over the sum of the two impedances times Vn. Multiply numerator and denominator by j omega C1 C2 over j omega C1 C2. In other words, multiplying by 1. Now the numerator, if we multiply this term out here, the j omega and C1 cancel, we're just left with C2. In the denominator, the j omega C1 cancels with this term, and we're just left with C2. And for this term, we're just left with C1. What we've got is that the voltage across the capacitor C1 is the other capacitor over the sum of the two times Vn. This is sort of like our conductance voltage divider of ECE201. This is happening because of the reciprocal relationships. The same thing is true about the voltage across C2. If you multiply through by this same 1, the j omega C2 cancels. You're just left with C1. J omega C1 cancels here, just left with C2. And then this other term here cancels with this, and we're just left with C1. So the voltage across C2 is the other capacitor over the sum of the two. Easy way to remember that, just like we are a resistive voltage divider. We don't have to rederive it each time. So a handy little thing to keep in the back of your mind. Now let's take our resistive bridge and let's replace the resistors by some capacitors. What we're going to show on the next page is that we can actually solve for one of these capacitors by varying a resistor. Again, suppose I vary this resistor such that this current is equal to 0, and that implies that this current is equal to this current, and so we have the capacitive voltage divider on the left-hand side of the circuit. So that implies that this current is the same as this current. I got a resistive voltage divider. R variable over R variable plus R sub s times V, a function generator, is the voltage across this element. But with no current here, I have no voltage across here because 0 times R3 is just equal to 0. So this voltage is the same as this voltage. In other words, the rise in voltage equals the drops around the loop. Take a look at that equation and see if we can solve for the capacitor C2 on the next page. Setting the capacitive voltage divider equal to the resistive voltage divider, we again have the function generator voltage dropping out. Do a little bit of algebra here. Let's divide by C1, numerator and denominator, so I get a 1. C1 divided by C1, and then C1 divided into C2. Do the same thing here, divide by R variable, so I get a 1. Then R sub s divided by R variable, and R variable divided by R variable. So again, we've got this term would have to equal this term. Let's write that down over here. Now if you cross multiply, I've got C2 times R variable would have to equal now C1 times R sub s. That again is our balance condition. Let's take a look at the previous page to see where is that on our bridge. When you have a balance condition for an impedance bridge, using a capacitor and a resistor in your bridge, the product of these two terms equals the product of these two terms. And the reason that's coming out instead of the cross arms is because of our impedance of 1 over j omega c, where the j omega term drops out. You don't have to memorize that, but I find that real handy when I'm doing things in lab for calculating stuff, without having to go back and look things up in the notes. Now let's just solve for the unknown capacitor, say C2. So then just taking this equation, C2 then is equal to R sub s times C1 divided by R variable. So if I can precisely measure C1 and R sub s and then set up precision resistors, I can again make an instrument that as I vary this resistance, I can calibrate the knobs on that to just give me the value of C2. Again, what's interesting here is this is all independent of the resistance R3. This is the resistor between the two voltage dividers. I forgot to mention previously, that's very significant because this would be the resistance of the meter that's stuck in there to measure the current. So whether the meter is ideal or non-ideal, it doesn't make any difference. R3 doesn't enter into the equation. So it's a very interesting instrument where we can make a very precise measurement by balancing a set of equations. Now this type of idea is actually used in a scope probe. Here's a photograph of the probe that we're going to be using in lab. It's a Digilent P6100. It's called a ×1 × 10 probe. It has the following equivalent circuit. In the tip of the probe, there's a capacitor of about 9 picofarads in parallel with a resistance of 9 megohms. There's also a switch where you can short this out. Talk about that in just a second. Then I have a coaxial cable, which has about 10 picofarads per foot of capacitance. There's a variable capacitor, and that's going to connect into our scope, which has, as we showed in the last lab video, an input resistance around 1 megohm and 24 picofarads of capacitance. Whatever appears across here is what we see displayed on our PC screen. Now when you put the scope probe in the ×1 position, it just shorts this out, and all you see then is the capacitance of the cable, really added to the capacitance of this variable capacitor, and then the input capacitance of the scope. So we effectively create a higher input capacitance than we had without the probe. Again, this does affect the circuit that we're measuring depending on the frequency and depending on the Thevenin resistance looking back into our circuit. So we measure a lot of op-amp circuits where the impedance looking back in the circuit is pretty low, so this won't be real critical, but as we look at other applications, we'll have to think about this. This won't show up much in ECE 203H. It will show up in some of our later lab courses. To switch open, we got this RC combination, and I really have here again just one R and a bunch of C's in parallel. Let's see if we can figure out how that matches our impedance Wheatstone bridge. Let's redraw that scope probe equivalent circuit. So at the tip, I have a resistance of 9 megohms, capacitor C sub A in parallel with about 9 picofarads. Now on the other side, I've got the resistance of the scope, which is around 1 megohm, and then I have 3 capacitors in parallel. I have the cable capacitance, the variable capacitance that's in the probe tail, and then I've got the capacitance of the oscilloscope, which is about 24 picofarads. If we draw this, it looks like our Wheatstone bridge. So here is C sub A, C sub B, and here is R sub A and R sub B. And I'm going to draw this connection that's in here as just a short circuit. We've got a voltage that we're trying to measure, and this is what's displayed on our PC screen. But if you balance this ratio of capacitors and resistors, in other words, if the product of this times this equals the product of this times this, then the current in this short circuit is equal to 0. Now with the values that we have here, what does that turn out to be? Well, let's take R sub B times C sub B equal to R sub A times C sub A. Bring the R sub B over here. And I've got 9 megohms times 9 picofarads divided by 1 megohm, and that's 81 picofarads. Total capacitance here with this variable capacitor needs to bring the value to about 81 picofarads. So we've got about 10 picofarads per foot with the cable, and we got 3 feet, so that's about 30 picofarads. Add it to this, and then subtract that from 81. That's what this needs to be equal to. But again, some of these capacitances are approximate, and so we can adjust that with a little set screw. Now, a variable capacitor is just a series of metal fins that are interwoven with each other. As you turn the screw, you can adjust the value of capacitance. They're not very big in value. They're really typically in picofarads. And obviously, that's what we need here. Now, when you do this balancing condition, you can remove this short circuit because there's no current. So instead of having a meter here, we just simply have a short. But what does that imply? Well, our displayed signal is our resistive voltage divider, which is RB over RA plus RB times the voltage that we're measuring, call that V out. But that has to also equal the capacitive voltage divider, which is going to be C sub A over C sub A plus C sub B times V out. But the ratio here with the resistors is going to be 1 megohm over 9 megohms plus 1 megohm, so it's equal to 1/10. The same is true with the capacitive value. What we're getting then on our display is a replica of our measured signal divided by 10. Now the disadvantage of the probe is that we're making the signal smaller, and so if we're measuring a tiny voltage, we're making it even smaller, and we eventually get buried into the noise of the oscilloscope. What we've effectively done is change the effective impedance looking back from our circuit. So we'll take a look at calculating that on the next page. So with the balance condition where we remove that short circuit, I have 2 capacitors in series, and that's some C equivalent, which would be our formula from ECE 201 of capacitors in series as the product over the sum. Now C sub A was 9 picofarads, and by adjusting our variable capacitor to create 81 picofarads total, that gives us a C equivalent of only 8.1 picofarads. R equivalent, again with the short circuit removed, we've got 2 series resistors of 1 megohm and 9 megohms, and that gives us 10 megohms total. Now before we put the probe on, the capacitance here was 24 picofarads and the resistance was 1 megohm. We've now decreased the capacitance and increased the resistance, and so we've increased the total impedance at a given frequency. So take a look back at Lab Lecture 2 and you can see the effect of these values compared to what we had before. So the disadvantage of the probe is that we're making the signal smaller. The advantage is that we're effectively lowering the capacitance and increasing the resistance to increase the total impedance of the equivalent circuit of the scope with the probe connected.